khona la Liberty College, as I previously said. You know how we do. Ask the correct questions, get the correct answers. Sabona sikunjani?
Ngiyaphila wena njani futhi?
Right, mina ngazako. What's your name? Where you from?
I'm Phemelo Udira and I'm from Liberty College.
Who are you?
Phemelo Udira.
Ah, Phemelo Odira. So your surname is Phemelo?
No.
Your name is Phemelo?
Yes.
Your surname is Odira?
Udira.
Udira?
Yes.
Like Udirang?
Not exactly.
Or what language is that?
Setswana.
Setswana? Oh, that's deep, Tswana, eh?
Not exactly.
Well, clearly I don't know much about Setswana, but I know physics. And what's your question for our teacher in this?
My question is, how do you calculate the electric field strength when there is more than one charge present?
Well, thank you very much for your question. Let's just quickly repeat it for our viewers at home. She asked us, how do I go and calculate the electric field strength if there's more than one charge present? So up till now, we were used to having a point charge and one big sphere that's got a specific charge, and that will influence the point charge. But now we're going to go that one step further, where we're going to have more than just one sphere with a charge present, and that means we're going to need to be using superposition to go and calculate the overall effect on that point charge. Now just keep into consideration that that point charge that we're referring to is just a little dot. It doesn't have a specific charge of positive and negative. It's almost seen basically like it is neutral. Okay, now let's quickly just take a look at an example as to what I'm actually talking about. So first off, we'll notice here's my little point charge, and I'm going to be having not just one sphere but two spheres that will actually influence this point charge. Now my sphere over here towards the left hand side is positively charged, and that for my right hand side is going to be negatively charged. Now when we are going to take a look at the adding up of these electric fields, we're going to need to bring about, in this specific case, a vector diagram to determine the overall direction of which these electric fields will be pointing. So you need to take into consideration that electric fields is indeed a vector quantity, so it's going to be having a size and a direction at the end. Okay, so the reason why we actually just take a look at one electric field at a time is if we take a look at the equation that we will be having, which note that the electric field is equal to K, which is the constant, times the charge, divided by the distance squared, we'll notice that this electric field equation only makes use of one charge at a time. But we've got, in this case, two charges. So that's our main reason for bringing about a vector diagram so that we can go and calculate both of them and then add them up. Okay, so let's quickly go and determine what is going to be the direction for the electric field for the positive and then for the negative. So when I'm doing that, I'm going to first take a look at one, completely forgetting about the second, and then take a look at the second, completely forgetting about the first one that we've had. So in this scenario specifically, there's my point charge. Let's quickly just forget about this negative over here. Then we'll notice that this positive will always make the point charge move away from the positive. Remember that that is the direction for your electric field. It's always away from a positive and it's towards the negative. So in this case, as you can see, goes away from the positive. If I then go and close up my positive and only take a look at the negative, then this point charge will be attracted then towards the negative, because we said it's away from a positive but towards the negative. So if I end up with these two now, both of them pointing towards my right hand side, I'll just go and add up my electric fields at the end. Okay, so that's it. Let's now go and take a look at a proper example from which we can go and end up calculating this. So in my proper example, what we're going to be taking a look at starts off by giving you a 4, which in this case is -4 nanocoulombs and -2 nanocoulombs. Now you'll notice now my point charge is not placed in the middle between them, but it's placed far to the right hand side. And you'll notice also that this is 1 meters away from the -2, but in total it's actually 4, or in this case 2 meters away from the -4 nanocoulomb 1. So first off, what we're going to do is we're going to take a look at a vector diagram, and then we're going to add the two up separately and then add them up as a total net electric field. Good, so let's first take a look at them separately. I'm first going to discuss my 4 Newton and my point charge. So note that, as we said, they're 2 meters apart in total. This point charge will always be attracted or moving towards a negative. That's how come in my case it's now going towards the left. Let's go and place in our values in our formula. Note though that K is a constant, and this K value will be given to you as 9 times 10 to the power of 9 at the back of your formula sheets. Note though that it was 4 nanocoulombs. Now we need to convert the nanocoulombs to normal coulombs by saying times 10 to the power of -9. Even if it was -4, we do not include that negative in my equation over here. We're going to leave it as a neutral value. And we'll then be dividing that with the total distance between them, which was 2 in total, and we still need to square that. So if you go and simplify that, we're going to end up with getting with 9 9 newtons per coulomb, and because in this case electric field is a vector quantity, our direction, as we said, was pointing towards the left-hand side. Good, so that's my first one. Now let's go and take a look at the second one and find its total electric field before we find the net electric field. So taking a look at number 2, which was now my negative 2 nanocoulomb one, we'll notice though that it is also negative, so therefore my point charge will be moving towards the negative. The distance though between these two is just 1 meter. So when I'm going to be filling in my values, still I'm going to have k, which is 9 times 10 to the power of 9. I need to convert the 2 as well to times 10 to the power of negative 9, and I do not include my negative sign in the front, and my distance, as we said, is just 1, and that needs to be squared. So at the end, simplified gives me 18 newtons per coulomb, and in this direction was also towards the left. Now when we add up to get to my overall direction and my net, we are going to need to know this type of formula off by heart. It's not going to be given to you on the formula sheet. So seeing that this, notice that both these two is going to have an electric field towards the left though, I'm going to then take towards the left as being positive. And my overall net electric field will be equal to the electric field of the 4 nanocoulomb plus the electric field of the 2 nanocoulomb. Afterwards, we will be punching in our values, and because I've taken towards the left as positive, I'll be using a positive 9 and a positive 18 as part of my values, which ends up giving me positive 27 newtons per coulomb, and that means the overall direction though was towards, in my case, the left-hand side. Okay, so that's basically for your superpositions of your electric fields. Something that I quickly want us to stand still as well is your superposition in 2 dimensions of your electrostatic forces. Now, 2 dimensions means we're going to have a vertical and a horizontal motion. So let's quickly take a look at a specific diagram, which hopefully is going to help you understand it a bit better. So you'll notice over here, I'm going to be having it in 2 dimensions. It's going to be moving up and down and towards the left and the right. And we would now need to go and calculate the net force experienced by the positive 6 coulomb charge. So this is my point of interest. From here onwards, we're going to take a closer look to see what's going to happen to the 6 compared to the 4 and between the 6 and the 2. Note though that these two things have got a specific charge. So between a negative and a positive, there's going to be a force of attraction. So that means if I take a look at my 6, it will be attracted and thus moving towards my negative 4. So this is my force due to the 4 on the 6. Then I take a look between the 6 and the 2. Notice also that this is a positive and the 2 is a negative, which means that my 6 will also be attracted towards the negative 2 and therefore will be pointing, in this case, upwards. So that's the force of the 2 on the 6. So now you notice that we're going to be having a force moving upwards and a force moving towards the left-hand side. But these two forces at this point is tail to tail. When we want to go and find the overall effect of these two forces, we're going to need to add them up, in this case, head to tail. So that's going to form for you a vector diagram, which is more specifically a vector triangle. So just to take you back again, notice how if somebody pulls upwards and towards the left, this object will actually be moving, in this case, right diagonally in the middle between the two. And we're going to find this value now by doing that vector triangle. So where we're going to first start with this force, right at the place where we end with it, we will start with our second force, which was the force of the 2 on the 6. And then to go and find this resultant force, we'll start with the very first force has started, and we're going to end where the last one has ended. And this is going to give me then my resultant force, which I'm going to call F res. And because it is going to be a vector diagram as well, I'm going to need to go and calculate that angle to determine for me what is the specific direction. So let's quickly go and take a look at the equations that you're going to need to use to end up calculating these two forces, because once again, I'm going to have a 6 and a 4 and a 6 and a 2. And once we've calculated them, we're going to do the net force calculation. And then after that, we're going to find the angle. So starting off here with my two forces. Force of the 4 on the 6, we're going to be using Coulomb's formula to determine it. Note that it's K, our constant, still the same, 9 times 10 to the power of 9. Then it's 4 times 6. We do not include the negative and the positive in these calculations. We leave them as neutral values. Divided by the distance. Now the distance was 4 centimeters, and to convert centimeters to meters, we'll be dividing with 100, and then it must still be squared. So simplifying it from there onwards, we're going to end up with 1,35 times 10 to the power of 14 newtons. Remember, newtons is the specific specific unit for force, and in this case it was going towards the left hand side. Now if we go back over to the 2 and the 6, we're going to end up here with a value of 2,7 times 10 to the power 14 newtons upwards, and when we place these things together, we'll notice we're going to need to find the resultant using Pythagoras. So therefore we're going to end up with 3,02 times 10 to the power 14 newtons, and because of the fact that I've got, in this case, the two sides, the opposite and the adjacent, we'll be using tan to go and determine my angle.
Snacks. Is that?
I have a question.
Ah, I have a question. Uba.
Helen Makakas.
Helen Makakas. Talk to the people at home, man. Helen Makakas, how old are you?
I'm 17 years old.
Are you sure?
Yes.
Oh, so cute. So what's your favorite meal from the canteen?
Doritos.
Oh, my chips in Japan.
Yeah, it's the only
Hey,
thing.
that's not a meal, Baba. Melutoli kota. And our chips, not a share. The pat, the white liver, the special, the snook, the archer.
Don't concentrate in class.
IT has never been a problem. So speaking of concentration, what's your question for our teacher in the studio?
I would like to know, how do I know in which direction is the electric fields traveling in?
Well, thank you for your question, Helen. Let's quickly repeat it for our viewers at home. Helen asked us, how do I know in which direction the electric field lines will point? Now, that's indeed a very important question, and I like to ask something like this, which luckily for you means easy marks. Now, your electric field lines will always have a specific direction, as we've mentioned in our previous lesson, and that was away from the positive and towards the negative. But let's just quickly stand still and remember again, what is the definition for the electric field lines? These definitions, like most of your definitions, comes actually at the back on your formula sheet. So it's made up from a formula. In this scenario specifically, for the electric field, the formula is going to be electric field is equal to the force divided by the charge. So it states though that it's the electric force experienced per positive charge that's been placed at a point. Now remember that these specific definitions you need to know off by heart, because they do want, in this case at the end of the year, to ask you quite a few of these definitions, which also means that you can go and make up your marks in sections like these. So let's quickly take a look at those electric field lines. We're going to first take a look at them separately. So as I said, it's always away from the positive and will be towards a negative charge. If I've got two separate ones, we'll notice though for the positive that these lines always radiate out at 90 degrees to each other. And you'll see that these lines never make contact to each other. That means basically they never touch or cross each other. Something else also that we've noticed from our game questions is if I've got a point charge like this, where it's a sphere that's radiating out, this electric field line is not uniform. That basically means is if I'm closer here, I'll experience a stronger field strength. If I move further away, it will be weaker. So that's how come it's not uniform. That basically means it's not constant. Now, as we said, for positive, you'll notice that the arrows point away from that positive charge. If I take a look at the negative, once again, it's still 90 degrees that it radiates out, but in this case, it's pointing towards my negative charge. Now, if I'm going to have a stronger electric field pattern, you'll notice though that we will have more electric field lines, and then they will be closer spaced to each other as well, but they still do not cross. So if I'm going to make my positive charge, in this case, a stronger charge, that basically means there will be more electric field lines to indicate that, and as we said, they are also closer spaced to each other. Now, let's quickly take a look at if I'm going to end up having two different charges, like two positives or two negatives. We know that if you've got two positives or two negatives and they're close to each other, they are going to end up repelling each other. And that's the most important part, which means that when we're actually going to see that, we need to see that there is going to be repulsion in the middle between those two charges. So let's see how we're going to end up drawing that. We'll notice though that if I have my positive charge and I take a look here basically at this side where there is no positive charge rather close by, the same happening on here, you'll notice that the normal electric field lines still look the same. They're going to be radiating out at 90 degrees and they are pointing away from the positive charge. And the same happens on my far right hand side. But right in the middle where these two is actually going to have an influence on each other, you'll notice that these lines actually bend away. although they still point away from a positive and they do not cross each other, they do bend away when they get close to each other. And that's going to be the same for my negative charge. As we said, two negatives will also repel, and first off, on the sides where there is no other charges that will influence them, we'll notice though that it will normally radiate out. So as we can see over here, it normally is going to radiate out, but in this case, it's going to be pointing towards the negative. And the last one is when there's going to be attraction. We'll notice it will go from the positive towards the negative, and now in the middle where there's the attraction, literally the lines is going to go from the positive and make contact here to the negative. As you can see, the arrows pointing as well from the positive to the negative.